Okay, let's go ahead and get started. Any questions before we jump back into algebra?
I can't hear you.
Sorry. Sorry. Any questions before we get started with algebra? Everybody have a good weekend? Yeah? And I don't know if everybody noticed, but Hope brought donuts. So you're having trouble getting your Monday going. There's donuts at the back. So thank you. That was very generous. So, all right.
Oh, thanks, Mom. I'm
You can slip back there as we work on our first problem. And if there are no questions, we'll just get right into it, okay? All right. So this week, we're going to continue what we've been doing with algebraic reasoning as we focus on patternings and extending patterns. And we're going to work on a pretty well-known problem called the Valentine problem. There are different variations of the problem. And then we're going to extend it to a very similar problem with handshakes, okay? So let's look at the Valentine problem first. So here it is, okay? And I just copy and pasted it from Blackboard to make it a little bit larger in a Word document. So each student, imagine you have a classroom full of students, okay? And each student gives a Valentine to everyone else in the class. How many Valentines are exchanged if there are 24 students total? So that's what you have to figure out. And then, of course, as we've been working on other patterns, right, you want to extend that to other situations. What if you had 30 students in your class? What if there were only 12 students in your class? You know, how does it change? What do we notice as the number of students change with the number of Valentines that are exchanged? Okay, so how would we, let's just talk together as a whole class, how might we begin thinking about such a problem? How could we model it? Georgia?
Well, if there's each of the 24 students receives 23 Valentines.
Okay, now don't go any further than that, because you're actually solving it, and you're doing that pretty abstractly, which is great. But everybody may not be quite in that place, right? Okay? What I'm asking is even simpler, right? If you were teaching third graders or even fourth graders, how might they model it?
24 minus 1? 24 minus 1?
Do you think they would, what would a typical third or fourth grader come up with? Why 24 minus 1?
You can't count yourself.
You can't count yourself, okay. I think you're both onto something, but you're still thinking like an adult, very abstractly.
They're not going to give themselves a Valentine?
No, that's right.
They might just
Yes, but how would they model? Let's say,
Chart.
okay, maybe a chart, right? Or what was this, Tricia?
I don't know, like pretty much having like lines to people.
Okay, they might draw a picture. That's a really common strategy for solving a problem like this, right? 24 is kind of a big number, isn't it? Another strategy is thinking of a smaller group, right? And then building up from there. We've used that with some of our other problems, even from the beginning of class when we did the taking away by ones and twos. If you remember, we dropped back to a really small number and then built up from there. So instead of 24, let's suppose maybe they're the same number of students that you have at your table, right? You all have it really easy because you only have 3, right? But we have some tables with 4 and 5. So how could you model that at your table? I mean, we're making it just as concrete as we can. These are, let's say, third graders. Yeah, I gave you some note cards. You could use those. These could be our Valentines, right? And everybody could take some Valentines and exchange them, and then so you could model it with 4 students. Why don't you do that now? And let's start a chart, because when we're working with patterns, we typically chart those results as a way of collecting the data, right? Does that make sense? What kind of information would we include in a chart?
numbers.
Okay, so the number of students. And we have tables with 3 students. Let's say we had a class of 3. We have 4 and we have 5. We have 2 groups of 4 and 2 groups of 5. So we can at least model these, right? What would our other column include?
Number of Valentines?
Number of Valentines or exchanges, right? So we can say number of Valentine exchanges. Right? Okay? So if there are just 2 of us, right? How many exchanges will there be? 1. 2, right? 2 exchanges. We each gave the other, right? And so see what you can find out. I'll fill that in if there are 2, there are 2 exchanges. Okay? So what happens if there are 3, 4, and 5? Do that at your tables. See what you come up with. You can actually physically exchange or just kind of talk through it. But your students are probably going to have to actually do it. In fact, I would encourage you to even have the model, you know, in front, just like I did with Ariana. Right?
I was just gonna make a chart. Yeah. I was like, where did we get that? So each person gets.
So there's only 3 of us. Okay, so exchange 1, exchange 2, 4, 5, 6.
You all will do it for a group of 5.
2, 2, 3, 6. We're trying to do all the
Gotcha.
numbers.
That's fine.
Wait. Did you give yourself one? 3.
No, don't give away yours. Those are the ones that you got. Don't give away one. That's a lot.
1. You guys finished quickly, didn't you, with just 3? Okay, our group of 3 is done. How many exchanges were there?
6.
6? And I know, Mallory, your group also did 3. You were working up, filling out the chart. Did you get 6 as well?
Yes.
For 3? Okay, excellent. How about any of our groups of 4? 12? Everybody that has 4 agree? Did you all get 12 when you exchanged?
Did you just give this?
Okay. How about one of our groups of 5? Haven't finished? I'll give you just a second to finish. And those of you who don't have 5 people, see if you can make a prediction based on what we know at this point from our data. Right? You give one to Hope, that's one exchange. If Hope gives one to you, that's another exchange. Does that make sense? So, you know, if you each give one to each other, that's not one exchange, that's 2 exchanges. So sometimes that has to be defined. I mean, yeah. Did you get it? What'd you find? Okay, 5 is 20. Okay, so one thing we've talked about as we've studied algebra is mathematical noticing, right? Is there anything you notice from the chart?
It's like times 1 times 2 times 3 times 1.
Interesting. So it would be pretty easy to extend the pattern recursively, right? So if I wanted to just add another one, this would probably be, you would expect it to be, this was times 4, this would be times 5. Good. And the next one would be 42 because it's times 6, and so on. And we could continue to extend recursively. We could go all the way to 24 students if we wanted, right? And you saw something, Georgia and Tricia, I think, initially, that you may have a student that sees that, and that's good, but you want to try to bring everybody up to that place. And so we're noticing something here and why that's happening. See if you can talk in your groups to determine how many Valentines would be exchanged if there are 24 students, and how you could write an explicit rule for determining any number of students, right? Whether it be 24 or 1,024. Does that make sense? What's happening as we exchange these Valentines, and how can we write that using a mathematical formula so that we can generalize? So I'll give you a minute to think about that.
I think this works. N is the number of students. You do N minus 1 and then you times N. So it would be 5 minus 1, 4 times 5, 20. 6 minus 1, 5 times.
I think that works. Would you put? Would it be N squared? I have to really minus 1. So would it be N squared?
So, I think most of you have a formula, right? What did you come up with?
Yeah.
Okay? Okay, x times x minus 1. So x being the number of students, I know some of you had n for this, and it doesn't matter what the variable is. And then this number is the product of this times x minus 1. So if we're looking at 2, 2 minus 1, right, is 1. 2 times 1 is 2. 3 times, so 3 times 3 minus 1 is 2, 6. We'll check one down here. 6 being x times 6 minus 1 is 5, 30. So what do you predict 24 will be? 552. And how did you figure that out? Yeah, 24 times 23, right? And if we do the math, not that I don't trust you. 452, is that what you said?
I said 552.
Wait, you're right. You're right.
Okay.
Just checking to see if you're paying attention. All right, so I did that so quickly. So let's see. Yep, 552. Is that what everyone got? Perfect. Okay, 552, and you are right. So 24, 552. How would you figure out, we won't do the math, but how would you figure out the 1024th example? Let's say you got a whole school of children who are going to exchange Valentines. How many exchanges, how would you figure out how many exchanges occur in a group of 1024? You got it, 1024 times 1023, right? Make sense? Okay. So this is the Valentine problem. At what grade level do you think students would be able to think about a pattern like this? 3rd grade? 4th grade?
I think they do it with smaller numbers, like earlier on, but then like,
Yeah.
as they get older, they get bigger.
Yeah, I think you could even do it with, say, 2nd graders, as long as you're working with really small numbers. You just won't analyze the problem to the extent that you would with older students, right? And you're going to see with a different problem in a little, at the end of class, how this can be, require pretty sophisticated thinking. So, Tricia.
Do 2nd graders, don't they start multiplication in 3rd grade though?
They do start multiplication. So how would they figure it out if they don't know how to multiply?
Repeated addition.
Repeated addition. And that builds the foundation for multiplication. That's a great question. So yeah, they're exchanging in their small groups, and let's say you have a group of 3. Well, I gave 2 away, you gave 2 away, and the third person gave 2 away. That's 2 plus 2 plus 2. We can use that in 3rd grade then to build on 3 groups of 2 is 3 times 2 or 6. So see how all those concepts connect and relate? That's really, I think, important. So yeah, we can just represent it a little differently and make it appropriate for students as young as 2nd grade. Good. You know, even 1st grade, I think there's some work that could be done just modeling it, right? Just beginning to help them think about it. And it's the problem solving, it's the thinking about the math that's more important than the actual computation and the correct answer. It's the problem solving. All right, so what we're going to do next is take a look at a 4th grade class. This is an Annenberg, whoops, wrong link. This is an Annenberg video. Going there. Okay, I actually have it pulled up here. So it's called the Valentine Exchange, and this is a bilingual 4th grade class. So we're going to look at how they process the Valentine problem that you just solved.
Annenberg reading. This is the Carrillo Elementary School in Tucson, Arizona.
Hey class, yesterday we had a Valentine party. Did you enjoy the party?
Lilia Olivas is a bilingual teacher at the school. Yesterday was Valentine's Day. Her 4th grade class celebrated the occasion by exchanging cards. This morning, Ms. Olivas is taking the opportunity to include Valentines in a lesson on patterns and functions.
If I have a Valentine and Gina has a Valentine, if I gave Gina my Valentine and Gina gave me a Valentine, how many Valentines have we given? Have we exchanged? Chelsea?
2,
2 Valentines. How is that 2?
because you had one, and that's one that you gave to her, and she gave you one, and that's 2.
What if I had 3 people exchange Valentines?
You'll have 6 exchanged.
We will have 6 exchanges. Could you show us how you came to that number 6?
If then I gave Gina one, then Gina gave him one, then Miss Olivas gave Gina one, then Gina gave her one, then you gave Henry one, and then I gave you one, and that would be 6.
Pretty good, huh?
I think Josefina's right. It'd be 2, 4, 6. ¿Por qué tiene que ser 6?
¿Quién le puede contestar a Winston? He says, why does it have to be 6?
Because I could exchange with you twice. Things like that. So it matters. So I could exchange with you and...
How many exchanges?
That would be 4 right there.
But if we were going to exchange 1 Valentine at a time,
Then it would be 3. Then I was right. It would be 2, 4, 6. It would be 4. And
How's
I
that
was
figure?
I give you 1, 1,
and how many is that?
2, 3, 4,
And
5, 6.
5, 6.
Do you see the range
Number
of
change
student
if there was
thinking?
4 people.
Why the modeling is important for some students?
Yes, but there would also be 4 Valentines.
You want to try it? Okay, let's try a volunteer. Chelsea. Can anybody guess what the number would be? Plus?
The answer would be 8 because you Denry and Chelsea, then Gina and Denry, then you and Gina, and then you and Chelsea. Oh yeah, but then Gina, it could be more because Gina hasn't changed with Chelsea and neither has Denry. Wait, 2, 4, 6, 8, 10. It could be 12.
Could be 12?
Yeah, it could be.
Let's try it. Gina and I will exchange. How many is that?
2. And then, oh,
What do they need?
4,
You need more Valentine's.
6,
Yeah, that would be helpful, wouldn't it? To model. What else?
The chart.
12.
Some way of keeping track, right?
12.
Have we all given Valentines to each other?
Yeah.
Does anyone have a different answer and would like to explain? Armando? Armando va a explicar.
What?
Okay. So how many Valentines do you have, Armando? ¿Cuántas Valentinas tienes? Okay. 12. There was 12 Valentines that were given with 4 people. Tenemos 24 estudiantes en esta clase y todos tienen una tarjeta.
Ms. Olivas now poses a challenge. If each student gives a Valentine to everyone in the class, how many Valentines will there be?
This is what I would like for you to investigate with your partner, or groups, or by yourself if you choose to.
I think the big ones should be people. And then the real little ones should be, Valentine? Yeah, Valentine.
Ms. Olivas encourages her students to select whatever materials they feel are appropriate to help them solve a problem.
The benefit is that you don't have a control situation. I'm not controlling their thinking. I'm allowing them to explore freely, to develop new ideas, to share, to reason. And that's what I want out of my students. I want them to be confident mathematical learners. Okay, I'm looking at what Winston has here. Okay? 24, again, what does the 24 mean?
24 people and 24 Valentines.
And you each had a Valentine, 24 people. If you started making exchanges, would there be 24 exchanges?
So we did 2, 4, 6, 8, 10, 12, 15, 16. It's 24. Then if all these people, like if me and Winston changes as 2, Las and another kid changes 4, another kid changes, another kid exchanges that's 2, 4, 6, 8, 10. See, there's 24 and 24. And if you add them both up, it's almost 48. That's probably not the answer because there's 24 people, and if this is 24, we do have to, like, Greg has to change with Luis, and then Luis has to change with this person. And Luis also has to give Greg one, so it's not 48 is probably not the answer. It's probably much larger.
Do you think this answer is too big or too small?
It's too little. It's too small because we have to, like, I have to give one to your store. I don't have to give one to me, so how about like this? That's 4 right there.
So you would consider changing this number?
Yes.
The questions that I concentrate on are questions that help them to think about what they're doing. I would ask something like, can you explain what these mean? Tell me what you're thinking. Tell me how you're doing this.
And what I'm doing is these yellow things are the yellow things are how many times they exchange. And if they exchange 12 times, they must have exchanged with everybody.
Show me how you're exchanging.
Well, I'm putting, okay, well, say I need to get this guy 3, and this guy has 3, so they both have exchanged it 3 times. And if I each pile them up to 12, they must have exchanged with everybody. Because I'm only doing 12 children. You get it?
There was a student that understood what was expected, then decided that he was going to do half of the problem. And even though the answer wasn't right, you know, he knew where he was going. He knew that there was a strategy involved. It was making sense to him.
So this is how I'm doing it. 48. What? Add up. 9 to 48. Okay, 2 times 25. No. Add 48 and then 9. Hey. But add it up over again.
So, Regina, could you explain how you thought about this? I'd like to know what the numbers mean.
This is like a kid.
Oh, these are the children?
Yeah, but then
So these are the children here?
yeah, those are the children.
Okay. And these?
Those are the cards.
The cards.
So then when this card exchanged with the 12, because it's like check.
Okay, could you show me how you're going to do that?
Whoever that was exchanged with the one that was making check right there. And then I would keep on going.
And when you counted all the squares, what does that mean to you?
That would be the amount if 12 people exchanged with 12 people.
What do you think about that strategy?
That would mean that
That
amount.
many exchanges, and then it would be
Okay. All students in this class have varied experiences, and the opportunities are there for students to understand at their own level of learning. And some students were not understanding, some students were partially grasping ideas, and some students like Josefina had grasped the concept. Okay, class, I would like for you to stop for a minute, please. I would like to talk to you about what you are learning. This is the time for questions, for comments. Okay. How did you feel about this activity, this process? Jenna?
Well, I felt at first that me and Adam were gonna come up with the answer good if we, cooperated and we didn't get mad at the paper and all that. And I thought that we could come up with the answer.
Gina?
I was confused in the beginning because I wasn't really sure what to start out with.
When I counted up each person, each table, there was, at table 1 there was 4 people, table 2 was 4, and table 3 had 3 people, and then table 4 had 4 people, table 6 had 4 people, and table 5 had 5 people, and then I thought I added it up and there was 24 kids, and I tried to divide it up, and I got 105.
With the total exchanges?
Yeah.
Well, I just got the little cubes and I started writing out people's names, and I said, well, okay, I'm gonna get 1 from Denry and give it to Adam, and 1 from Adam and give it to Denry, and then around the class, but then I got messed up and then I had to start all over. It's really hard.
Josefina?
If you had 24 people in your class, you would give a card to each person, but instead of yourself, so you would give 23 cards out. So 23 cards, so you times 23 times 24, and then you came up with 552.
The whole focus is, how are you thinking about the problems? How are you making sense out of the information that you have on the table? How is it making a connection in your mind? What are you looking at as far as strategy building and problem solving?
Okay, so what did you think about the lesson? What did you notice? Any aspect, the mathematics, the structure of the lesson, just anything at all? Georgia?
I think the way that she modeled it confused them.
Okay,
I think them exchanging the same cards and not collecting cards when they exchange them threw them off, and I think more kids would have been successful if they had modeled it.
okay, very good, yeah. And Mallory, you mentioned that too as we were watching the video. Yeah, I think you make a really good point there. Yeah, because they didn't they were very concrete in their thinking, yet when they modeled the exchange, they didn't end up with the correct number of cards, right? Good. What else?
That was interesting how the kids cut the number in half, so it's like a small number for the number.
That is a really great strategy, and we need to model it. The strategy I'm talking about is solving a simpler problem, right? So 24 is a big number. It takes a long time to pass out, Valentine's to 23 kids if I'm the 24th student, right? And then I've got to consider that for every student in the class. I haven't identified a pattern yet. That's going to take a long time to model. Well, let's do it with half of that number, right? Or even a fourth of that number, right? Let's work with maybe 3 students. That really is, and we want students to have enough practice with using that strategy that they think of that on their own, right? This student did. Did you see the range of abilities in terms of their problem solving and critical thinking? Yeah, there really was a big range, and I think that everybody was able to participate in the lesson at a different place, right? What else did you notice about the lesson?
It challenged them.
Some more than others, right? Yeah, for sure. What about the materials? What did you notice about the use of materials?
Let them pick what they wanted to use as their mentor.
Yeah, they got to choose. What, do you think that was a good decision? Yeah. Some of them you may have noticed were more abstract in their thinking. They were able to draw a picture. What pictures did you notice? What visuals were prominent in the within the group?
Those are the kids that had tables drawn.
Yeah, so the table drawn and little circles for the people sitting at the tables. They could kind of think about the number of Valentines, write that number that's exchanged by that one student, and record that in the circle and do that, and maybe identify a pattern, right? Great visual model. What else did you notice in terms of the way they were recording on paper?
Chart.
Yeah. What did the chart look like? Which chart are you talking about?
And let the numbers down the side and
Yes.
across the top.
Good. Yeah. So here are all the names down, right? And here are all the names across the top. So, I exchange with Kinnaman, I exchange, and I go all the way around, right? With Shauna and Hope and, all the way around. Do I exchange myself there? Because there is an intersection with my name at the top and on the side. Do I count that one? No, I don't give myself a Valentine. So they begin to see a pattern within the chart. That's a great way to visualize what's happening in the problem. You could accomplish that with an even smaller number though, right? And begin to see what's happening. Okay? What were some other strategies? Well, there's one that they did not use that I think would be really useful. And we're doing this because we're going to do solve a problem in a minute called the handshake problem that I think is considerably more difficult to think about. And so hopefully some of these strategies will be useful to you as you explore that problem. Okay? So, was there one that they didn't use that you think might have been useful? We've kind of alluded to it. Emily?
Well, I think if in the very beginning when they did the exchanging of the paper, if they would have had each student go one at a time and then hold up the number of times they exchanged,
Oh,
and then
okay.
just go down the line, that would have made it a lot easier to see.
It would have made it more obvious, wouldn't it? So if we've got 3 students and I give one to you 2, right? I'm going to hold up, or get them to hold up the Valentine that they have. When we're done, we're going to each hold them up. Well, there are 3 of us, we're each holding 2 Valentines. Well, what if there were 4 of us? We model it. Now how many are we holding up? 3. There are 5 of us. How many are we holding up? 4, right? We're beginning to see a pattern, and we record that data. Recording the data is really important in the chart because that's where the recursive nature of the pattern becomes obvious. And we use that to then begin to write a rule. What I didn't see was, and Tricia, you alluded to it at the beginning, you were doing this, right? You could draw a picture, right, with the circle as the table, and then if I'm exchanging Valentines with all of you, I'm going to draw a line from myself to Kinnaman. I'm going to draw a line from myself to Shauna, right? I'm going to draw a line, right? And then from Kinnaman, what am I going to do? Draw a line, draw a line, draw. And so you get this, really intricate drawing. You can count the number of lines, each one representing an exchange, right? Does that make sense? Yeah. What did you notice about, one more question, then we'll move on. What did you notice about the structure of the lesson? Was it problem-based? Yes. Were you able to see before, during, and after? Yeah, it really was structured that way. So before, what did the teacher do in the before?
She
Modeled it with a smaller group, they exchanged the Valentines, there was some discussion. That's where you make sure students understand the problem, right? Then what did they do in the during?
They were allowed to use any group if they wanted to solve the problem.
Excellent. What other choices did they have? Yeah, they could work in small groups, they could work independently if they wanted. She really gave them a lot of freedom in terms of how they went about solving the problem. They could do it with another person, with a small group, by themselves, using manipulatives, drawing a picture. I mean, it was completely open-ended, right? But they were working, that was the problem solving, and then what was the after like?
Discussion and sharing.
Yeah, discussion, sharing. Some students were able to think all the way through it, others were still working on it, right? But they shared where they were at that time at the end of the lesson. That closure is really important for processing the mathematics. Okay, so I just wanted to point that out. So we've been talking about problem solving or problem-based lesson planning all semester. And it's really simple. I mean, and how many problems did she go over? One. So if you get a really rich problem, a really good problem like the Valentine problem, that takes care of the planning for the problem-based lesson plan, right? You think about it, you're getting them ready to do the problem, they're doing the problem, then they're processing the problem, right? Yes?
Do you think it would have been helpful for her to say something like, if your parents are buying Valentine's, how many Valentines do they need to buy for you to give out to your friends? Help them realize that they didn't get a Valentine? Or do you think that would be too much?
I think in the beginning, it might be too much. I think the more open-ended you can be in the beginning, the better, because you don't want to stifle their ability to think of that on their own, right? But I think if they're struggling and they're not making that connection, there are things like that that you can say that will lead them to it, and I think that's appropriate. Yeah, great question. I think as a professional, you have to make those decisions, right? When are they ready for this information? The least you tell them in the beginning, though, the more opportunities you provide your students to problem solve. And as the teacher acknowledged in the end, it's more about the problem solving than it is about the mathematics. The math is important, but if they become good problem solvers, they'll figure the math out, right? If they are not equipped with these strategies and the ability to tackle a problem, then they're really limited in what they can do mathematically. Okay? All right, you ready for the handshake problem? All right, we're going to get started with this in class today. I don't know that we'll finish it, but we'll see. All right, so here it is. Let me just copy and paste it into this Word document. So it's a little bit bigger. All right, here we go. There are 20 people in a room. Okay, if everyone shakes hands with everyone else, how many handshakes will take place? So with no modeling, because we're building on what we learned from the Valentine problem, I'd like for you to talk about this at your tables. If you would like manipulatives, I'm going to put some blocks out up here. You're welcome to use those. You have your cards. You have your hands if you want to You know, however you want to model it. I've probably said too much, okay? That's up to you. You may want to record on paper, but take about 10 minutes, see what you can do with the handshake problem. Yeah, so Hope asked a good question. We've got to make sure students understand the problem before we let them go, right? So what constitutes a handshake? Yeah, so if I shake hands with Hope, right?
That's one.
That's one. Whereas with the Valentines, it was two. We each gave the other a Valentine, but when we shake hands, that's one handshake. So see, it is a different problem. Okay? Good question. Good question. Have tiles and counters. If that's helpful, it may not be useful, but feel free to come up and take them.
Nine? So he's like,
Oh,
So this is your guess for 20.
Well, one night. Because that was the
6, 7, you'd go 8,
yeah, but we can't
I don't think so.
and then
I'll go quickly. I know because like, I just don't have the answer.
she's already,
yeah.
It's different. Remember the strategies we used for the other problem, right? That is actually So all you did is okay, perfect. See if you can solve it another way.
Okay.
Yeah. I hadn't even thought about it quite like that, but yeah, good.
okay, so then there's 4 of us, and then I'd go 1, 2, 3.
I think I knew we would have it. So I like just did like number 1, and then I thought about it like I think I might have. Okay, so I took like there's 20 people. I've been giving names. Everyone gets 19. I know they crossed it. Four of us. Okay, so then I got 1, 2, 3.
And I go 4, 5.
That's not how I did it.
And you go 6. Okay.
So
That's
just,
way easier than how I did it.
yeah, 4 other numbers and see if it works on every time.
Okay. And I'm also confused, like, I get how to do this, like, make charts and stuff. I'm like, this is the algebra form.
Yeah, yeah. So how can we, this is a good question, then, how could we write this as a formula? So if I didn't care about 20, maybe I wanted to know if there were 50. Also, I'm thinking, how would I come up with a formula? What, see, the only way to figure that out is to focus on the relationships and the numbers, right?
for not just like Thomas, but
What you did is you put something in, I don't want to go back to this. Remember her formula before this was in? Well, this was in. This was in minus 1.
You sure 5 is 9?
yeah, because what
Yeah.
say there's 5 people sitting
Think
next
about
to
it.
us.
And I would even just,
So
yeah,
1, 2, 3, 4, 5, 6, 7, 8. Yeah.
oh,
And
and
10, that's why.
smaller numbers.
Yeah, so it's 10, and then this is 5.
And you get
15.
Oh, my brain is not working.
Because that was in a separate
You come up with a solution? Okay. Okay.
It's like I can do it, but I don't know how to explain. And like they're not.
Well, this goes on one
Yeah,
list,
like
and then
the
there's
rest
like
of
people there are.
And
Yeah.
like, so like, if I'm gonna divide 3, divided by 2.
Well, the first one does it. And the second one does it. But one person is
21.
just ignore the first one.
I mean, you related it all to what we did in the previous problem?
I think it's it's something divided because it's half. Because each time
I don't understand that
it's
way.
however many people
I like the one allowed.
times something divided by 2. Like there's
There are lots of different ways and strategies to go about solving it. No?
I'm stuck.
So you are adding,
See if you can relate it to the previous
one
problem.
more,
Do you notice any similarities?
you're adding one less there.
I mean, this one goes up. Wait, so there's 5 people?
Yeah. But do you notice anything like here? These numbers.
Oh, they're
what's the original formula? Because you don't get you give to Valentine's
Times 100.
I don't get it. Okay, so the actual fund, 5 is 35.
How are we doing?
9 and 4 is 30.
So,
And 8 and 3 is 25.
The whole thing.
Ah,
That helps her. Does it? I just
is it?
Did you guys find another way to do it?
No.
To model it?
Okay, cool. I knew I had to have provisions.
So you know what you're thinking.
So, I was just saying, like, so 1, you're not shooting into anyone, and so 2, you're doing 1, and 3, you're doing 3, and then 4,
I wouldn't have.
like, if that sticks, it got up to 6, and then it got kind of confusing, because then I was like, it's not well, I knew it had correlated with the last problem. Unless it's just supposed to be. And I did one,
Just every time. Why?
because each time when me and you shake hands,
Exactly right.
it's always one. You said
Where's mine?
So then that is how you would get that.
And you know, if you're modeling that with a small number, like let's say you have, let's say you have one's not gonna shake hands with themselves, those two shake hands, that's one. They shake hands, two. They shake hands, that's three. Let me start with this one, that they've already. Right, so then you have. So where we had 3 on the first one, then it's plus 2, and then again, you don't go back, because they've already done it, and then it's 4. So there is something to that, so it's 4. So another way to write it.
I was like so surprised because I got an ounce in the wine and I got like, well, this, I was surprised. The rest of
But
it.
you don't need to use it.
The old word.
But we know, we're seeing that.
Oh, yeah.
Got it?
Yeah. So it's the same formula as last time, but then divided by 2.
Why does that work?
Because when we shake hands, that's only one interaction. So it's the same thing, but you have to divide it by 2 because each time there's a word shaking.
There's one word.
Good, good job. Is there another way you can solve it?
I was thinking,
Yeah. We're gonna go ahead and talk about it, so.
Yeah, I think I'm supposed to do an outline first.
I'm gonna go ahead and stop you.
Who does it?
In the interest of time, yes, I will, I'm not gonna tell you the answer, but we're gonna share some of our solutions, okay? And you all process this in different ways, so who would be willing to get us started? Anybody be willing to come up and share what they know about?
Oh my God.
No one?
I'll do it.
All right, come on up, Lydia.
I don't even know how to explain it. I can see it in my phone, but I don't know how to do it.
See, I'm not sure the light is
So
on.
I got that.
Let's see what we can see. Okay, that's good. Zoom, I think. Everybody see that?
Okay, so basically what I did is like, each person is gonna have a 19 exchanges total, not including yourself. And then I really don't know where this came from, but I said 19 times 20, because there's gonna be 20 exchanges, right?
There are 20 people.
20 people, yeah, okay, 20 people. And then I did 19 times 20, which would be 380, and then you divide that by 2, because there's 2 people. And then I got 190. And then right here is my equation. So it'd be x in parentheses, x minus 1 in parentheses, and then divide that by 2. And I don't know if it works like every time with other problems, but it worked for this one. So.
Okay. All right, why do you think that's working? And Leah, you can tell us, or anybody else that solved it, because several of you used a formula like that. What did you notice? Why did you, I mean, x times x minus 1 looks familiar, right? Where's that coming from?
Valentine's.
Valentine problem,
But
right?
that you have 2 exchanges, for this you only have 1. So you
Okay.
have to divide that by 2.
All right, so exactly, so that's one way to solve it, and it's hard to convince students that that will work. You can try that with a smaller number. Usually what students will do is they'll begin to fill out their chart, right, with the number of students and then the number of handshakes, and some will notice a pattern, a similarity between that data and the Valentine data if you solve the Valentine problem, okay? But that clearly works, and the reason we're dividing by 2 is because instead of 2 exchanges, there's only 1, right? It's 1 handshake. All right, good, good. Who solved it in a different way? Okay, come on up.
My handwriting is trash, I'm sorry.
Oh, you're fine.
Okay, so I'm like, it's like sloppy and kind of weird. Can you guys see that okay?
It is hard to see. I wish I
Yeah.
could get these lights to come on, but they're not.
So I was like thinking about it, and like, this is person 1, so like person 1 would shake hands with person 2, then with 3, 4, and like went all the way down to 20. And then I was thinking about
like when person two, like instead of listing them all out, I just thought, well, two already shook hands with one, so then it would like reduce down one number, if that makes sense. So it's like person one has 19 handshakes, two 18, 17, 16, it just goes all the way down to 20, and then I added them all up and got 190. Does that make sense?
Yeah,
Okay.
that's great.
I didn't come up with a formula though, because like, I have no idea.
Can you, that's okay, can you, just while we're looking at this, how did you add all these up? Did you literally add 19 and 18 and take some of that and add 17, punch them in a calculator?
I punched in a calculator, yeah, I wouldn't do it by hand.
Okay. Is there a fast way to do this by hand? Yeah, there's a pattern here, right, that we can utilize to make our addition a little bit easier. We can add 19 to 1, that makes a group of 20, right, cross those off. 18 and 2, another group of 20, 17 and 3, 16 and 4, and group them in 20s, and we can count by 20s pretty easily and do that math in our head, right? You'll have students that see that, and I would choose that student to come up at the end of the class, thank you, Megan, and share their thinking, because that pattern is going to manifest itself, in other situations. And so you want them to notice it, right? We talked about mathematical noticing. That's something for them to notice. Okay, what else? Anybody do it a different way?
Yeah, I did.
Okay, come on up.
Alright, I'm gonna try to explain this as best I can, but I just like writ out everything. So, real messy, but.
That's okay.
Alright, so these are like explaining like there's 4 people in a group, 5 people in a group, all the way down to 20.
Okay.
So then I kind of figured out like the first like 4, 5, and 6. So I knew it was like 6, 10, 15. I started finding a pattern that like every time you add a person to the group, like the difference is 4, and then the difference would be 5, and 6, and 7, and then it keeps going. And then, this is where it got pretty wild. I looked at the difference between 10 and 5, and that difference was 35. And then I looked at the difference between 9 and 4, and that was 30. And then 8 and 3, and that was 25. So then I kept finding the differences going down, and then I knew once I figured out 15, I know that there's 85 more than what 15 is going to have, and 15 was 105, so then I added 105 and 85 and got 190.
Wow. That's awesome. But see, you just generalized.
Is that right? That's right.
Yeah. Yeah. Because what he was able to do is look at patterns further down the chart, right?
Yeah.
And make some generalized statements. That's great. Excellent.
Thank
You may have a student who really thinks about it in that way. Now, we could explore why that worked, right? And could we extend that to another set of numbers? Excellent. I think that's excellent. What else? Anybody do it a different way? Do you understand why it worked, Jason?
Yeah,
Justin?
yeah.
Yeah.
I was surprised I could even explain it, but
No,
I think I did a good job explaining it.
you did make good sense to me. Yeah. I mean, you're just looking for patterns, right? And then you notice with the differences there were patterns, right? And you found the differences of the differences and kept going out. And that allowed you to take, a larger set of numbers, right, and extend it further so that you could get all the way down to 20. Perfect. Great reasoning. Do you see what's happening here, though? The level of reasoning and critical thinking, the problem solving, is just as important as the problem itself. So could you figure out if there were 1,000 people in a room and they were going to take the time to shake hands with every other person in the room? Could you write an explicit rule to do that? In fact, some of the groups did that in the beginning. Yeah. So it's basically the Valentine problem, n times n minus 1, divided by 2, right? Now, do you think this problem would have been a lot more difficult had you not solved the Valentine problem?
Yeah.
I agree. I agree. So, let's see how we're doing on time. We've got just a few minutes left. I'm going to pull up some examples very quickly of student work. And let's look at how students might process the handshake problem. All right. So let's take a look. Manuel says, I think this problem might be kind of easy. Oh, you can't see that, sorry. Here we go. He says, I think this problem might be kind of easy. There are 20 people in the room. Each person shakes hands with everyone but himself or herself. So each of the 20 people shakes 19 hands. So it would be 20 times 19, or 380 shakes, handshakes. Okay, what do you think?
That's incorrect.
Okay. Where did he go wrong?
He's counting 2 people, whatever he's.
Right, he's counting, one handshake between 2 people counts as one handshake, right? He's counting 2, so he's doubled. But does he understand the problem at all?
Yeah.
Or is his reasoning valid? Yeah, he's just not quite there. All right, let's look at what Beatrice did. She said, well, I decided to look at a smaller case. Okay? I thought, what if there were 5 people and I drew the lines connecting them? Kind of like what you did, Justin, right?
Yeah.
Okay. Except we've got them in a circle here. What do you think about that method? She says, I counted the lines and there were 10. So then I thought, what if there was another person there? I thought that this person would shake 5 people's hands, so there would be a total of 15. The 10 ones from the old people and 5 ones from this new person. And I thought, well, what if there was another person? I started to get confused, so I made a table. And that's important. It's important for students to realize, instead of our telling students, all right, here's your table. So often, remember at the beginning of the semester we talked about structured and unstructured problems? And so often our textbooks give us that table, right? And it tells us how they're labeled, and it says fill in the table, right? We need students to figure out how to generate the table, first of all, based on a need to keep track of the data, right? The work we do with algebra is intricately involved with data analysis. And so we've got to have a way to keep up with that data. And so it becomes purposeful when they decide that they need a table, right, as Beatrice did, okay? So here's her table. And what she started looks very similar to what Justin was doing, right? Finding the difference. I put this one here because the new person adds 5 handshakes. And she starts to notice, oh, it's a difference of 5, 6, 7, and so forth. I understand how my pattern works, but I don't know how I could use it if the numbers went up to 1,000. Okay? All right. Here's Carmel, or Carmel. Carmel. I think it's probably Carmel. All right. My way is kind of like Beatrice's way, except I started right at the beginning. With 2 people, there is 1 handshake. Then with the 3rd person, you have to add 2 more handshakes. With the 4th, you add 3 handshakes. The 20th person shakes 19 hands. So you have to add up all the numbers from 1 to 19. I found a shortcut for adding up all the numbers. That's what we talked about, right? Good. I grouped them in pairs that added up to 19, except I left 19 by itself. Now what could Carmel have done that would have made this a little bit easier? 20s, right? Grouping them in 20s. So adding the whole numbers from 1 to 19 is the same as adding 10 19s, because there were 10 groups, so that worked, or 190. Okay? Okay, Katia. I made a chart and put an X. We've seen this one, very similar to the Valentine problem, right? So, but what do you notice that's different? How does this chart look different from the one we saw in the video with the Valentine problem?
It's cut in half.
Cut in half, exactly. So, we know you know, A doesn't exchange with A, right? You don't give yourself, you don't shake hands with yourself. So then we've got A shaking hands with B. But when we get to B shaking hands with A, they've already shook hands, right? So we don't need to record it, so you get a diagonal look, yeah. They have to really think about it. So those were the solutions. So the same solutions you came up with. Now, I will tell you, if students haven't solved the Valentine problem, the handshake problem is very difficult for them. So beginning to see those relationships and building, even if they do the Valentine problem in 3rd or 4th grade, and then in 4th or 5th grade, they build on it. If they've done it using, you know, they've been given the freedom to figure out how to solve it on their own so that it really does stick, they will remember that problem. Oh, I've done a problem similar to this, and they'll be able to apply it. But if they've never seen the Valentine problem, the handshake problem, really, I've seen it become very challenging, not just for elementary students, but for university students too. So it's something to think about, okay? What we're going to be doing next is looking at how we take these patterns and generalize that explicit rule that we've been talking about in the form of a function. So we're going to talk about what functions are in the next class, and the last 3 classes are going to deal with functions, okay? And then we'll wrap up what we've been doing with algebra. Now remember, Wednesday, you've got something due, right? Remember, what is it? Video reflection, right, by midnight. So don't forget. Any questions about that? Everybody's doing okay? All right, very good. All right, we're going to stop right there, and because we're at a great stopping place, and then we'll pick up with functions on Wednesday.